words about the today's event. The event is today's in the first speaker will be Professor Archon Mishra from Singapore Management University, and Dr. Brojeshwar Bhomik from TCS Research, India. They are the two speakers of today, and two session chairs of this event will be Dr. Himadri Pal, TCS Research, and Dr. Professor Siddhartha Bhattacharya, the chair IEEE CIS Kolkata, will chair the today's two technical session. May I now introduce and invite Dr. Himadri Pal to chair the first session of today's event, entitled. The title of the event is. Okay, the session chair will announce that. Let me invite Dr. Himadri Pal. He is working as a senior scientist at TCS Innovation Labs, Kolkata. Dr. Pal completed his Bachelor of Engineering from Jadavpur University in 1996 and Master of Technology from IIT Kanpur in 1998, PhD from IIT Kharagpur in 2004 in all computer science and engineering. He has worked in reputed industry houses like Silicon Automation Systems and Interest Systems India Private Limited. He has also worked as assistant professor in computer science and engineering at IIT Guwahati. Dr. Pal has widely published in the areas of distributed systems, fault tolerance, cloud computing, and Internet of Things. His current researches focuses on robotics and its reliability and safety. So let us move forward to the first lecture. Title is optimizing perceptual machine learning on edge devices by Professor Archon Mishra. And to chair the session, Dr. Pal is to take over the session. Yeah.
Thank you, Professor Mukhopadhyay.
Yes.
It is my honor to introduce Professor Archon Mishra for this talk. Professor Mishra is the Vice Provost of Research and Professor of Computer Science at Singapore Management University. Professor Mishra has provided leadership to a number of multi-million-dollar large research initiatives at SMU. These were collectively developed into an initiative of a mobile or wearable computing technology for urban computing applications. He is the current recipient of the prestigious Singapore NRF Investigatory Grant for Sustainable Human-Machine Interaction Intelligence. He is also a program co-PI of the recently launched M3S program with the MIT on advanced human-robot collaborations. His current research interest lies in the ultra-low energy execution of machine perception algorithms on IoT and edge devices to support advances in natural human-machine interactions. Professor Mishra has over 25 and more years of research experience, both in academics and industry. He worked with IBM Research and Belco. Professor Mishra researched and practically developed many technologies which spans wireless technologies, mobile and wearable devices, sensors, urban mobility analysis, and etc. He's the ACM distinguished member, and he has chaired IEEE Computer Society's Technical Committees on Computer Communications from 2005 to 2007. And Professor Mishra will be delivering a talk today on optimizing perceptual machine intelligence on edge devices. So I invite Professor Mishra to start the talk. Thank you.
Thank you, Professor Paul. I assume you guys can hear me clearly enough. Can I just confirm that?
Yes, Professor Paul.
Okay. The screen sharing is disabled right now. You might just want to enable that because I cannot share my screen right now.
Okay, just a moment, sir.
Sure.
Could you please try it again, sir?
Yes, I think it's working fine. So you should be able to see my screen now.
Yes, sir, it is visible.
And the one thing I want to do is to change the pointer option to a laser pointer, just because it's easier. Okay. Well, first of all, my sincere thanks to the Computational Intelligence sort of Society for inviting me. And beyond just the talk that I'm about to give you, I think it's just a great initiative. I want to congratulate all of you for just making this, getting started, because building these communities and sort of exchanging ideas, even if you do them virtually, is just fantastic. And it's kind of like the kind of growth that I would really want to see, not just in Kolkata and India, but certainly globally as well. So again, thanks for the introduction. I'm going to be talking, my plan is to talk between 45 and 50 minutes. I'll try to keep to time. It's 9:10 now, so I mean, where I am in Singapore, so I should end on the hour, so in about 50 minutes, just to give you a heads up. And if I'm running late, please, Professor Paul, just give me a signal, although I will try to keep within 45 to 50 minutes. So, as I introduce the talk, it's going to be on two different things, but I'll just parse out some of the keywords over here. So it's perceptual machine intelligence. Edge devices, I think all of you know. So machine intelligence is essentially the idea that you're going to be running some kind of perception or decision-making algorithms that are automated. So when I say perceptual machine intelligence, in both of these cases, I'll talk of two different use cases today. They'll both be about executing perception algorithms. And obviously, today, almost all perception is kind of using DNN models. So I will be talking of DNN-based execution of perception. One will be around visual perception, and particularly around object recognition tasks and how one can accelerate them. That'll be half of the talk. The other half of the talk will actually look at something called multimodal instruction comprehension. So this is the case where you might be instructing a robot, yes, go fetch me that glass of water, or pick up that blue pen next to the bookcase in front of which the dog is sitting down. Something like this, where you're actually going to be issuing natural instructions, which we normally do to other human beings. And the way we do that is through a combination of verbal cues, sometimes gestures, sometimes eye gazes, or facial expressions, and certainly also with visual cues as well. So these are kind of the two different paradigms I'll talk about today. I wanted to acknowledge at the bottom that a lot of the work is actually being done by a variety of PhD students and postdocs over here at SMU. And the last thing that I want to say before I move on to the next slide is, this is not a talk on machine learning. It's actually a talk on optimizing the inference algorithm. So nothing in my talk is actually going to, well, that's not entirely true, but largely the talk is not going to be talk about learning approaches. It's not talking about building a model or training a model. It's really about when you want to execute the model during the testing or inference phase, how do you make it run faster, consume less energy, and so on. So that's sort of the background in which I wanted to put this. Now, one slide on edge computing. Again, I don't think you need a lot of introduction to edge computing. I'm assuming most of you today kind of know what it is. But there's some interesting data points. When I first started tracking, this is a slide obviously from around 2017 or so, the one on the left that you see over here. It's the paradigm shift that I think is really important to point out. So around 2017 or 18, about 70% of the data generated, digital data generated worldwide, would actually end up hitting a data center, whether it's the photos you click or the data produced from cameras, et cetera. It would all end up at a data center. And only now, over time, this is around about 2017 or so. Again, but now by 2022, this was the prediction that 70%, the situation had flipped. 70% of the data generated actually doesn't hit a data center. It's consumed on the edge. And that's because there's just so many devices out there generating so much data that and in many cases, again, this is not a talk on the motivation for edge computing, but in many cases, initially it used to be a bandwidth story. That story is perhaps less important. Then there was a privacy story. You don't want to transfer a lot of data back to a cloud, but with private clouds, et cetera, that story also has become, in my view, less important. But the one story that stays constant is the latency story. So it's the need for sort of real-time perception, because you want the system at the edge to respond to events that are happening, to instructions human beings are issuing, because you want to preserve the interactive feel. And if you want to do that, you kind of need to cut down the latency and therefore do the processing at the edge. The other sort of big picture idea, let me just give me a second to move this. You probably can see it. It's just the screen that I have. So the big picture idea, and again, this is borrowed from a handbook that is publicly available on the web. So if you think about the sensor data supposedly generated by 2032, again, we always take market numbers, not as sort of a very precise ground truth, but sort of an approximate ballpark. But if you look at it, it's actually saying there'll be 1 trillion zettabytes of sensor data, 1 trillion zettabytes of sensor data generated by 2032. And the more important point is, and this is why optimizing the inference task is important, that a huge percent, they say 80%, it's 80 plus, I think 90-95% of data is actually unnecessary, it's uninteresting. And the quote I often tell my students is, sort of our day-to-day lives, it's a reality that most of the time in our lives, nothing happens. And that's a great thing, because, we don't want all the excitement of outliers and sort of, accidents and sort of memorable incidents happening all the time, because by definition, they're rare events. So a simple example would be that if you put, a window glass break sensor on different window panes in your house, for example, and you have maybe a microprocessor that's detecting vibration or sounds or microphone, whichever modality you want, and you're looking out for that one glass break because of an earthquake, because of a burglar coming in, etc. But the reality is more than 99% of the time, the sound is actually irrelevant sound. It's not the sound of glass breaking. Even if it was the sound of glass breaking, it's more likely that you're breaking a glass in your kitchen as opposed to somebody actually breaking the window in your the glass in your window. So what this illustrates is really the need to optimize the unnecessary computation at the edge, and that's what I'll be talking about today. A couple of different approaches that I'll be discussing. So the other observation I would make is, just broadly looking at where the AI industry and all of the people doing sort of the actual model building are going. So if you look at this graph, for example, again, this is a graph just about sort of feature extractors for visual perception. And this axis is the number of parameters in millions. And you will clearly see that over time, the number of parameters is increasing because we're building deeper models, novel architectures, transformers, and so on. But one of the interesting things that this paper pointed out, don't look at the accuracy. The accuracy is obviously going up with each of these models. But the y-axis is the accuracy per joule. So per unit of energy spent, how much accuracy do you get? And what do you see in that? What you're seeing is every new model incrementally moves the accuracy needle, but it actually spends a lot more energy doing that. So the accuracy per joule metric is actually going down. So this suggests that there is kind of a sustainability challenge, that we're going to be spending, one of the things I've just been sort of observing talks, et cetera, just like this one on the internet. And there was this fascinating talk, excerpts from the CTO of one of the major companies who actually projected out. Now, this is pure projection, which I don't think is correct. I mean, correct in the sense it's a little bit alarmist and it's probably not going to happen. But if you just project the energy spent in sort of AI and data processing algorithms right now, and you project it out to 2050 or so, if we continue at the growth rate that we've had over the last 10 years, if indeed the growth in energy consumption continued that way, then computing and AI model execution would actually, the total energy would exceed the entire world's energy production by 2050. Entire world, fossil fuels, solar, whatever nuclear capacity installed, it would exceed that. So you clearly see that this is kind of an unsustainable path. And so one of my research objectives is to try to reduce the energy that is being consumed, trying to use simpler models to get the same accuracy in some cases, or to optimize the execution of models. So that's kind of the overall framework that I'll talk about. So at the edge, you have all these choices. When you have the cost versus complexity trade-off, you can upgrade the edge. You can go from a Nano to a TX2, etc. So you have more powerful devices, and obviously you can run more powerful models on it. But you can also use smaller models, but they come with the accuracy trade-off. So that's something that I'll talk about. Or you can implement a variety of strategies like early exit, model merging. I'll give you some examples right after. You can also downsample the input resolution. Now, for example, if you have a 4K image that you're processing with the DNN model, it will take, about 20 times more energy than if you're processing a 512 by 512 image, simply because you have less neurons, less computation to do. Now, again, there is an accuracy trade-off, right? Once you downsample the input resolution, you're losing sort of features in a vision frame. So you have to be careful about that. But these are all different choices that have. But downsampling, and I hope I'm just sort of teasing what I'll talk about a little bit later. Within downsampling lies the possibility that if you downsample an entire image, again, taking the basic principle that even in an image, when you're driving a car, it's the same notions of perception that we use. Not every pixel in your field of view is you're paying attention to, right? Because you're only focused on objects closer to you. You're maybe not focused on peripheral objects at a certain time. So if you kind of downsample, not just the input, but you down select the computation that you do, and you intelligently down select it to focus only on areas that are kind of salient or important, then you should be able to get a much better sort of accuracy per joule budget. And that's sort of what I'm going after. And today I'm going to talk in the next 30 minutes or so, very high level breadth first exposition on the first one, which is kind of do more with less, which means you take one edge device and you have multiple vision streams or video streams, and you want to use the same edge device to process all of them concurrently. And the only way you can do that is that you do selective computation. You don't compute over the entire stream. The second thing that I'll talk about is sort of the collaboration, the notion that you often have sensors laid out in somewhat redundant or overlapping or correlated configurations. So if you imagine, say on the TCS campus, you have cameras that are monitoring. I can say with a high degree of certainty, the campus security cameras actually have overlapping fields of view. So there's certain parts of the physical environment that are actually being witnessed by multiple cameras simultaneously. Even if they're not overlapping, they have temporal correlation. So you see a car at the main gate, 5 to 10 seconds later, it's going to pass by another car on the way at another checkpoint or on the driveway, for example. And then I'll talk a little bit about multimodal comprehension, which is kind of the more exciting future direction or ongoing direction of my work. I do want to spend a little bit of time about this exciting M3S project, which was mentioned in my introduction, but I'll give you an overview of what that is. Okay, so now that I've set this up, the next 30 minutes is going to be sort of 3 different aspects. I'll talk of Mosaic, I will talk of COM AI, and then I'll talk about a couple of multimodal comprehension algorithms. So you're trying to optimize the edge inference for using object detection as an exemplar task. There are some strategies. All of these are well known. This slide just illustrates some of the well-known strategies. So you have early exit strategies. So early exit means that you basically train a model to have multiple points of exit. And if you're very sure in the early stages, I mean, if you're very certain that this particular object you're detecting is a cat, you can short circuit a lot of the computation and just declare early on if you have a high confidence. So that's going to save you on average, minimize the average latency across an ensemble, but you need to modify the model. The next thing you do is kind of DNN slicing and cloud overload, offload. So an example is, algorithms like neurosurgeon, et cetera. You take a DNN and you cut it at some point, and you're trying to balance the computational cost versus the cost of transferring the state of the neural network, the intermediate state of the neural network that either in latency or energy, whichever your metric is, or a combination thereof. And you kind of want to optimize between what you process locally versus what you do on the cloud. Finally, there are variations of DNN modification as well, which I call differentiated computing or amortizing. Again, I'm sure you can look these things up. These are kind of well-known techniques. But amortizing over multiple tasks, this is model merging. So if you have 2 different tasks, each one has a neural model, but you'll see that many of their layers are actually common. So if you can create a common base layer and then just spin off little heads that are variants from the base layer, you're obviously saving the total computation cost. So these are all examples of where you're kind of modifying the model itself. Having said that, so what I'm going to talk about is you take off-the-shelf models and you don't modify them. You just modify the processing and runtime, because I'm not an AI person. I'm kind of a systems AI person who looks at how to optimize the processing of AI systems. So let's take the example one edge node. You imagine 5, 6 cameras, either in your lab or in your campus or your housing estate, whatever, and you want to process them with a single edge device, because you could have 4 edge devices. That's expensive. So the simplest approach is you have 4 independent instances of the DNN, and each one processes something independently. Now, if you do that, it stands to common sense that the throughput of each camera's processing is going to be 1/4 the capacity of the edge node, right? Because you're going to kind of do a time division multiplexing across the 4 instances. Now, you could also do something like, you do first come, first serve, for example, or you could, there's basically a contention of resources. You could do batching. So batching effectively, if the sizes are the same of the frames, etc., you have the capacity, you kind of batch them together and you execute at the same time. But this is not the most optimal, because you kind of uniformly downsizing each of the images. So what you see so one of the things I wanted to point out again over here, if you look at 2 models, YOLO V3, a much smaller model with operating on a much smaller image size, YOLO V5, much larger image size, and you look at the total inference time, you see like a factor of close to 70 to 80 difference in the inference time. So clearly there's some advantage if you can continue to use smaller models and still get the same kind of resolution, same kind of accuracy at the end system. So in the end, what we see is seemingly, if you look at the seesaw, we have a choice. We can either use a larger GPU, use bigger models, but that has more energy, etc., or we can use lighter models, but then you get lower accuracy. So the whole point is, how do I kind of bridge these two and do this something called criticality-aware processing? Now, there is a series of work that my students I have done. The purpose is not to go over all of them exhaustively today. I'm just going to talk of one exemplar and then sort of point you to other examples. So the work I'm talking about is Mosaic. And the idea is going back to the same use case that I wanted to say, which is this use case. You have multiple streams. You want to process them with a single edge node, and you want to maintain the high throughput that possible. So can we extract and pack only critical regions? So the way Mosaic works, the core concept is something called canvas-based processing. So what are we doing? We are taking these, in the previous example, I showed 4 different camera streams, could be image or video streams, and I'm going to fit them all into one single composite image stream. So I'm going to create a virtual image, one single virtual image out of 4 images. So that's called a canvas. Now, what is the notion of a canvas? The notion of a canvas is like with an engineering approach, you're first going to figure out, so you see the example over here, that for different canvas sizes, which is the virtual frame size, you get different throughputs. Because the smaller it is, you get larger throughput. So depending on your application, if it's a real-time traffic collision detection application, you might say I need a throughput of 24, 30 frames a second. So you look at the point and you say, which is the point where I'm above this throughput, what's that size? And that determines your canvas size. So the canvas size is basically something that is just optimal, because at that point, you can just meet the minimum threshold that you have in terms of processing throughput. And this will vary by platform to platform. You kind of have to profile that. So the methodology that I'm going to talk about today is actually going to be identifying regions of interest across these M cameras. In the example I talked about previously, M is equal to 4, and kind of fit them, do some spatial bin packing into a virtual frame. And the objective is multiplicative increase in the processing throughput. And you want to process, because I'm processing 4 streams simultaneously, so I should get 4 times the throughput, but I don't want to sacrifice the accuracy. So conceptually, here's how Mosaic works. Imagine there are 4 drones. For now, imagine there are over 4 non-overlapping areas. Okay, so this is actually an example with 2 drones. So I process the 2 things. I first figure out very cheaply, because processing time is important, that these green regions are the regions of interest. It's not that I know exactly where the person is. Maybe I have to look for a person of interest. But I say that the rest is background uninteresting. And this I can do relatively fast. Then I take all of those things, which I call tiles, and I fit them onto a canvas. So now you see the notion, these are tiles. I'm extracting subregions from different images and packing them into this virtual frame, which I call the canvas frame. And you could do this with 4. The more you can pack in, obviously the higher gain in throughput you're going to get. Now, this core idea seems simple, but I want to give you a little bit of, some of the sort of novel mechanisms one has to put in place to realize this in practice. So in practice, first of all, the natural question is, what is the size of the tile? We talked about this tile over here. You'll notice these tiles. What are the sizes? So it turns out there's no perfect answer. And for that, you actually have to profile. You look at each camera, because depending on the deployment, cameras will end up seeing. So this is like a sort of a scatter plot of the object sizes seen by the camera with ground truth annotation. And you see there's a range of different objects, and it all depends on the type of objects. You could see human beings, you could see elephants, you could see cars. They're different sizes, but it also depends on the perspective of the camera. Sometimes they're closer to the field of view, sometimes farther away. So you basically take this and you kind of fit a model to find out a few clusters. So this is a classic clustering, and you say there are a few representative, and you can do this in unsupervised manner, and you find 3 clusters. And you find these 3 values. These are 3 XY sort of bounding box values that are representative of a large number of objects or profiles of objects. And you define tiles like that, and then you define a larger tile, which is, this is more details. The key point is we do not, again, I emphasize, you are not just partitioning the image into a set of tiles. The reason you can do that is then you're going to split an object. If it's a large object, you're going to split it across multiple tiles. And sometimes you might drop some tiles or squeeze them, you'll distort the object, and the DNA detector actually won't recognize. So what we do is we take the input frame, and what this animation shows you, this is like a tile maybe at 36, 39. Then we also create tiles at slightly larger scales. Remember, these are redundant in some sense because they have an area common with the smaller tiles. So you get a series of tiles at different scales. Once you get these tiles, you apply them over, so the object is contained in potentially multiple tiles, you get a bag of tiles. But after you get the bag of tiles, then you kind of run through this is a kind of the heart of the system, you determine the critical tiles. So to do that, okay, there's some optimization because you want to run this fast with some spatial quad tree, you find which are the tiles with intersecting and common sets of objects in them. Once you determine the critical tiles, then we want to do this, select the best subset. So what does a best subset mean? So for example, you see here, there are 2 tiles. When one small tile, this person is contained. In a larger tile, you have 2 images. So there's 2 sort of conflicting objectives. Ideally, you want to take very small tiles because you're wasting less space on background regions. Because this large tile, you see a lot of space wasted in background regions. Now, this tile is arguably better, but if there are many objects, you're going to get many, many, many small tiles. Instead, there might be a tipping point where it's actually better to take one single tile instead of 2 small tiles and have both objects be contained in one tile. So there is some sort of optimization algorithm that looks at the size of the objects relative to the size of the tile, and it's kind of a sort of a zero-sum game. You ideally want larger and larger tiles, but tiles that have, at the same time, that minimize the amount of background wasted space. So that would be the best combination, and you kind of create some metrics, and on the basis of that, you end up selecting a set of tiles. And you'll see that you can end up with selecting 2 tiles, and ideally, this person is not contained here, so this is best because there's no redundancy, but sometimes that redundancy is inevitable. And these are across field of views. Then you construct a canvas with the 2D inverse bin packing algorithm, where you're resizing all the tiles within certain spatial bounds because you want to pack them into the canvas, because maybe there are like 50 different objects right now in the frames. You can't pack 50 tiles directly in this canvas, so you have to resize and kind of squeeze them in so that they fit. And this is how the end canvas looks like. Now, this is obviously an illustration, and there are various optimization algorithms. I say genetic over here, you can do this with various other algorithms, so that's kind of less interesting. So here's the end result. I'm just being mindful of time and going right to the end result. So we have 2 different data sets. This is a drone data set. You can see it's looking at objects from sort of a bird's eye view. This is actually a data set of real world cars and vehicles. And here the goal is to do license plate recognition. So first, let me focus on this. So x-axis is the frames per second in camera when you're packing 6 camera streams. This is, you're packing them as 6 camera streams, and this is the accuracy MAP score at, mean average precision score at 50% IOU. And what you see is you see FCFS, which was the first come, first served. You can get about 6 frames per second because you're splitting up the total processing load among the 4 cameras, and you get 0.8, which is the highest, because you're giving, in each frame, you're giving it entirely to one camera. Now, but you look over here with the sort of tiling strategy that we have taken, each camera is actually getting 23 frames per second. It doesn't get 24 because there's some processing overhead in doing those extraction pieces. So you lose just a little bit, but you get 0.78 instead of 0.8. So you have lost a little bit of accuracy, but you're now much closer to real-time spot processing. If you get the outputs, it's very smooth. And your cumulative frames is 23 times 6, it's 128 frames per second. So you've gotten 475% increase in throughput with about less than 1% drop in your accuracy. And that's pretty good. Now, I want to give you the same example because you might question, oh, that's good for object detection. But if you're doing things like license plate recognition, and this is where, again, this approach turns out, this is actually the character error rate. And the first come, first served approach, because you're processing the whole frame and you are squishing it in an content unaware fashion, this actually has even higher error rate if you're going to squeeze it into a canvas frame, because this car becomes like a much smaller object you can't read. But here I'm actually able to fit 3 different camera streams together and get a character error rate, which is about 28% or so, which still means I can recognize the license plate overall. So again, you get a much higher throughput, and in this case, you get a much higher accuracy than what we were talking about. So that's kind of like the overall summary. I mean, I could go on more about numbers and so on. There are variants of this. What I just talked about in the canvas frame, you'll see I had, at a time, 6 frames come in from 6 different cameras, and I was processing and fitting all of them. But if you want to talk about real-time perception, this is actually something where, for example, you want to do collision avoidance, etc., then the metric you want to use is called streaming perception. So streaming perception has to balance accuracy and latency of object detection. I'll be very brief here. So the whole idea is you look at this, you get this frame. This is where the object is in this frame. It takes you T2 minus T1 time to process, and then you declare a bounding box. But what is happening is during that period, the yellow thing is the bounding box, the green one has moved. The object actually has moved. And so the basic philosophy is for real-time perception, it is not enough to be accurate. You have to be fast. And sometimes if you're so slow and you're very accurate from an application point of view, it's completely useless because the object has moved on. So therefore, we handle a few variations, all based on the mosaic concept, which is you handle overlapping camera views where you look for redundancy in the same object, maybe from different cameras, and you incorporate scheduling. So the whole idea over here is, again, you look at these 5 cameras over here, and what you do is you extract frames from the same object, but at different resolutions from different points of view, and then you do an admission control. The difference between this approach and the previous one is admission control, where you say, some objects I'm not even going to schedule because I don't have enough throughput processing capacity, and I have recently localized that object. So it's better for me to skip it because by slowing down computation, I'm going to lose on an overall real-time streaming perception accuracy. So this involves on a frame-by-frame basis some additional admission control to support real-time perception. So there are some variants over here. I will really skip it, just being mindful of time again. But what you see is what it does for a streaming average precision, which is a metric for real-time perception. You can actually go up significantly by applying this result, because the basic approach of going sort of first come, first served is terrible because you're processing frames, you're falling behind, and in the end, they're totally useless. You're doing a lot of useless processing. So that concludes the first part. Where can you do more with less? So now I talk about another piece, which was the collaborative intelligence, which is motivated by the fact that you sometimes have where you're running these DNN algorithms on the cameras themselves. These could be cameras embedded with some lightweight AI processors. It could be, various kinds of neural processing sticks, etc., attached to them. Now, the whole idea, what I earlier showed was that from an energy per accuracy per energy, it is better to use smaller, lighter models because they're more efficient that way from an accuracy energy combined metric perspective, but try to get the same accuracy. Now, again, here you see the pipelines. These are two different cameras. And for the sake of argument, imagine this is your campus layout. You'll see examples later. The cameras have partial overlap. They're not fully overlapping. That would be pointless. But they have partial overlap, but from different points of view. And each of them has their own DNN pipeline. And so the whole point that we want to illustrate here in terms of collaboration, I want to give you some extremes first. So one extreme is, why not pass both images? So each DNN actually takes two images instead of a 3-channel image, create a 6-channel image, and then run a DNN. So you have to modify obviously the DNN model, you have to train it, but it should do better. The whole idea is, suppose you and I are sitting in two different perspectives and trying to look at a particular scene, a wild animal. So sometimes you may see things fuzzy, you may see some features. I, from a different perspective, may see certain features. So neither of us individually may have high accuracy, but if we kind of combine our eyesight together, then we should be able to improve the accuracy. And that's the whole idea at this point. But this is a kind of a silly idea because you're going to have to transfer raw images from one to the other. That's very bandwidth intensive, terrible for energy. Now, the alternative is, why don't we just look at the outputs and do kind of a late fusion? Yes, one can do that. This is classic sensor late fusion. You can do sort of soft combining algorithms and so on. But it turns out that this approach is not very effective because if both of us have blurry vision, then it happens that by the time our detection comes, we both say there's nothing there. Even though we are kind of uncertain, we're not entirely sure, but we have come up with a binary output and it's too late. So what we're trying to do is to actually exchange things from the intermediate states of the DNN. That's kind of the novelty, the novel idea. And the even more novel idea in what COM AI finally does, and this is the key insight. You have typically a pipeline with multiple convolutional layers, some pooling, softmax at the end, and NMS, right? Non-maximal suppression. Anyway, even from the very first convolutional layer, if you look at the feature maps being activated, there are enough hints. It's not precise, it's not good enough for a final detection, but there are some hints that suggest that I may have seen an object. And therefore, I can use a very shallow classifier to translate this to your field of view. There's a spatial translation happening and give you some hints that I think I saw an object. And I do this early. Why? Because it takes this amount of latency to transfer the state over the network. But while I'm transferring, you are actually doing processing. This is a non-blocking execution. So the throughput of processing of each is completely unaffected because they're taking hints from an earlier layer, which has been processed in the past, transferring it over that network, ideally just in time to boost confidences and modify confidence values before you hit the softmax layer. That's the core idea. Now, this core idea, again, a lot of details, but I'm just giving you some evidence that this idea works, and then I'll give you the final results. So here you see an image, and you look at different feature maps and the activation heat map values, and you see that even in the first few layers, there's actually correctly identified persons. It's not a perfect bounding box, but there's enough sort of going on there, say there's an object of interest. Now, every now and then, you will have false alarms. You will do false positives, and maybe this was a tree. If you kept processing, you would not think this is a human. But right now, you generate some activation values. But the key point over here, why does this system work, is that you see this example. There are these two people walking together from this point of view or from this side. They're clearly separable because they're side by side. But from this camera, one is occluded, so you can't actually view them. So examples like this, maybe the background is confusing to the foreground from one point of view. Maybe the lighting from one side has high reflectance or is dark. All of these can happen in real world. So that's when you begin to find things. Now, in terms of the opportunity for combining, there is also one very obvious thing. And what I wanted to illustrate over here is the error CDF. I'm sorry, I can't actually view this with the confidence values. And what you see with the CDF is that larger the objects. So you have these various sort of different boxes, right? Anchor boxes of different templates for objects. So larger the objects, you're more confident. Smaller objects, you have less confidence because you kind of can't see the features. So it seems the logical thing to do is when you're passing hints, you don't pass hints on every object, everything you detect. You only pass hints for things that you see as large, that you suspect the other guy might see as small. And that's the only collaboration needed. So if you are seeing something from a far off point of view, I'm seeing it from a close by standpoint, I want to pass you my hint. The reverse approach is usually not useful because my accuracy is pretty high. So this is an example where this guy can pass hints to this camera because this one is a smaller object, you may be less uncertain. So I'm going to skip this. This is kind of describes the entire approach of how you select, how you train the model with the gradient boosting machine. It's a very shallow network, so it doesn't add latency. And what it does in the end, this result is important. So you see this x-axis is processing latency, and y-axis is f-score, or some measure of accuracy, let's say. So you see if you are standalone over here, you have two choices. Your two choices are you can use SSD and you get low latency, but you get much lower accuracy, or you use a deep model like YOLO V4, much higher latency. It's less than 1 frame a second in this particular case, but you get higher accuracy. Whereas what we've done over here is actually we are using SSD models. We're no longer using the deep models, but they're collaborating. But by sheer virtue of their collaboration, and this is with real world data sets, you have got the same latency benefit, yet you have actually beaten the accuracy of a standalone deeper model. So I think what this illustrates, the reason this is interesting to me is, we've always had this belief in sensor networks or sensor network operation, that it's important to do as much processing locally, and communication is way more expensive and should be avoided, and you should do processing locally. But when it comes to very large objects like images and high volume streams and very complex computation like DNNs, then there is actually an emerging paradigm where carefully chosen modest amounts of communication. In this case, you see that it takes less than a few kilobytes of overhead, 1 kilobyte per frame of communication overhead. It actually gives you a boost. This is a better operating point because networks have gotten faster, more energy efficient in communication, whereas the processing complexity keeps going up. So a modest amount of communication actually helps us eliminate or focus or optimize significant amount of computation. And that leads to not only latency gains, but energy gains, etc. So that's sort of the other piece I wanted to talk about. Now, finally, in my last 7 minutes or so, if I may, I will talk about this human-robot interaction piece, which is the other model of what I call perceptual machine intelligence. And with the Apple Vision Pro, etc., coming up, we're quite excited because they'll give us real platforms to demonstrate some of the things we're talking about. So let me give you two first use cases. So the use case on the left is you're wearing some kind of smart glass. You're walking in a supermarket, grocery store, and this is just an embodiment of a virtual assistant overlaid on the smart glass. And you point and you verbally ask the question, what is the price of that red jam bottle? Now, the whole point is the glass should be able to use your pointing gesture, your verbal input, do a visual analysis of the scene, and be able to extract which jam bottle you're talking about. So it needs to do object recognition, needs to identify which one is red in color, but it also uses the pointing gesture, which may not be very precise. It wants to do all that and give you back an answer. It says, once I look up the object, then I can look up a catalog, a price, an inventory of it, and give you back an answer. Another example, and this will connect to the MIT project that I'll talk about in a bit, is the ability of humans to work with robots together. In this case, the perception module is actually on the robot. The robot, it may not be a smart glass. This may have a camera, may have LiDAR, may have microphones, etc. And you're saying, oh, get me that blue wrench. And there's a cluttered sort of factory operating scene. So which object are you pointing at? So it's the ability to disambiguate your instruction. And your instruction is given in natural language with gestures with a lot of potential ambiguity. So one example of such ambiguity is perception ambiguity. You say, can you pick up the object on the left? Now, even to a human instructor, it's ambiguous because it's not clear, is it your left or my left? But sometimes the pointing direction makes that clear. So these are cases that you kind of have to reason. And this is what I mean by multimodal human instruction understanding. Now, we want to optimize that. Again, why do we want to optimize this? Because we want to create interactive robot systems or interactive sort of spatial computing applications. The reason we want to do that is that because it's multimodal, the core DNN module, so this is an example of something called RealGAN, which is a one-stage module. I need to explain this a little bit. So here you see you have a RGB image. You can even have a depth camera input. So typically what happens is and then you have the verbal input, which you have converted, say, into a text stream. So that goes through, again, in the olden days, you could have an LSTM, a GRU network. You're extracting features. You're similarly extracting features at different scales using some kind of object feature detector extractor, right? But then you kind of come to this adaptive feature selection where you use the odd verbal features to then go and say that I want to increase the attention I give to certain parts of the image, because ultimately it's a fusion. And you do that at multiple layers, then you have a global attention mechanism, and that's how you end up doing what's called the target object recognition. So an example is here you point, the robot is on the other side, and I say, pick up that green block. There are actually multiple green blocks, but somehow through the combination of verbal, pointing, visual reasoning, sort of processing, you apply a bounding box and you say that this is the green box I need to pick up. Then the robot does the job. So again, just to separate out, my group's research has nothing to do with the mechatronics of the robot. It is all about converting verbal instructions into a precise, what I call a task ML for the robot. So the coordinates of the object, maybe the sequence of path that the robot needs to take, then the robot will go do its job. So there are two sort of big paradigms that we've looked at to try to optimize these, because these models are very complex. If you try to run them right now, if you actually try to run the model on a HoloLens, it cannot fit, it cannot run. So we still kind of run them on a Jetson TX2-like device, but I'm pretty optimistic. I mean, it can run on a phone, but it cannot run on like a HoloLens-like wearable device yet, but we're kind of getting close. So there are two basic approaches. One approach is, you give instructions and I create multiple models. You have to train them separately of different complexity. So by saying different complexity, I mean I can create a light model, super light, ultra light. So the ultra light model may not even take pointing gestures into account. So the key observation is, you're giving instructions, but different instances of the instruction have different either verbal complexity. I can say, pick up the red box, or I sometimes say, pick up the red box behind those yellow boxes, which is next to the vacuum cleaner in front of the TV. That's a much more complex verbal instruction. Or sometimes the visual scene is cluttered with multiple red boxes. Sometimes the visual scene only has two boxes. That's it, one red, one green. So then you don't need to do all the complex processing. So you build a sequence of models, and the key thing is you use something called a complexity processor, a predictor. This is a pre-processing unit with just a 2-layer CNN. It predicts which one should I switch to. So this is basically a multiplexed architecture. You have all the 3 models, and you just dynamically switch between them. And here is the end result that I wanted to show you. RealGAN is the basic model, 80%, 82% accuracy. With our approach called Cosmic, we lose accuracy. Yes, we do. But what we gain is, look at the energy. We have reduced the energy 4 times. We've improved the latency by a factor of 3, etc. These are average cases. Remember, because this is dependent on the instructions, the task set, the corpus, but it reduces the overall average energy or latency. The downside of this particular approach, why it's not attractive, is you have to keep all three models in memory, otherwise swap them in and out. So it's not that efficient in terms of memory. So yes, it reduces energy and latency, but it requires larger memory. So then comes the last sort of technical piece I'll talk about. Can we improve this even further by having, if you will, just a single model and doing sort of dynamic skipping of different layers? And indeed we can. This was a piece of work in last year's multimedia, where the idea is that, remember I took these verbal, let me go back to this diagram, actually this diagram first, just indulge me for a second. So I have these verbal features that I've got. Now the question is, you see these, you are processing the visual features at different scales, smaller scale, larger scale, very large scale. But I can use the verbal features as hints and theoretically first actually avoid computing certain visual scales. Let me give you an example. If I say pick up the vacuum cleaner next to the fridge, you probably don't need to do the smallest visual scale sort of feature extraction because the fridge is pretty large, vacuum cleaner is pretty large. On the other hand, if I said pick up the phone next to my eyeglasses, then the smaller visual scales are important. The larger visual scales, probably not. So I can skip certain visual scales, and that's the optimization we can do. But that approach I just described is what's called the hard skipping. You actually skip certain layers. If you notice the title of my talk, it's soft skip. Why is it soft skip? It turns out that there are certain types of instructions, and I'll give you an example. Pick up my glasses, which are next to the fridge. Now, what do? The glasses object is actually a small object, right? So finer scales are important. But there is a hint there next to the fridge. The fridge is a large object. You need the larger visual scales. So it turns out that the best way to do that is not to entirely skip a scale, but to approximate it with a lighter computing path. So instead of like a 10-layer neural model here, I use a 1-layer DNN or 2-layer neural network, a perceptron model, to do a sort of soft approximation of that scale. And this is good enough. So don't completely skip, but approximate visual scales. And there's some sort of training trick, etc., for this model. But I want to show you the end result. So RealGin is the model that has sort of the highest accuracy. This is the unoptimized model with 350 milliseconds over here, right? Whereas with our approach, which is this LGMDP, the soft skip model, look at my accuracy. I've lost less than 1% accuracy, but I've actually saved about 60% or 50% of the this number doesn't show it, but in other cases we save about 50% of the latency, and we actually save even more of the energy on average by doing these kind of skipping, dynamic skipping algorithms. So that's what I wanted to illustrate over here. So I hope, this is kind of the end of the technical part of the talk. In this particular illustration, we have different data sets. We've saved 33% latency, but less than 1% loss in accuracy. So again, you're improving the inferencing pipeline. In my last 4 or 5 minutes, I want to tell you a little bit of what is exciting, what is coming down the road. So first of all, we talked about vision processing, and we think we can optimize the DNN, etc. But as a systems person, you always ask, are there other types of approaches? And indeed there are. So one of those is the use of these event-based vision sensors. So if you're not familiar, go look up neuromorphic or event-based sensors. And what they do is that they do not capture frames, but they only fire individual pixels with +1 or -1 whenever the intensity changes. So it's kind of, think of it like a delta encoding of whenever the intensity changes. But these things can operate at much higher frame rates, 10,000 frames a second, etc., and much lower energy. So these event-based cameras actually have between 10 microwatt to 10 milliwatt of energy as compared to the tens of milliwatt for even the best RGB frame-based cameras. So we can reduce the latency even further, but there's some problem. These event-based cameras have been shown to be very good, in these accelerator models where you're tracking objects, or if you're doing a super high horse race or a rocket firing, because you need to track the motion vector. But they do not give you color information. They do not give you texture information. And so their performance with spiking neural networks as the mechanism is actually inferior to DNNs for objects for tasks such as object detection and tracking. So the message I'm about to give, can we combine both? So this is what I'm trying to show you. Exploit the joint power of both of these sensors through a joint perception pipeline. So let me just draw your attention over here. Imagine you have both cameras. You have an RGB camera and an event camera together, just kind of fused together. The RGB's advantage gives you color, shape, but it's higher energy, and it exhibits motion blur because its frame rate is not as high. Event camera, very high frame rate. It's robust to motion blurriness, but doesn't capture texture and color. So one of the things we've been doing is combine both to do a very low power, low bitrate video encoder. Now, the way it works, I'll leave you with the very high level ideas. So I take one image. Suppose you want 30 frames per second video. So I take one image only using the RGB camera. I extract the key points. There's some things called MonkeyNet and other DNN algorithms. You extract the key points and you pass those RGB key points together with the original frame back to a generator network at the receiver. The receiver has more energy, more computing power. And so what it does, conventionally, once you pass the key points, it will, because you're passing the motion transformation of these key points. And it's not just translational motion. It could be rotation, it could be warping, because it's my face. You give key points, my face is changing, right? My chin is sort of warping. So you pass those, but the generative network then produces, the video generator produces the output at 30 frames a second. But now what we do is we only capture one frame here, but we capture maybe 100 frames using the key points from the event stream. We convert those key points to a simple lightweight transformation network into RGB key points and send these RGB key points. So these RGB key points have not been obtained from the RGB image. They've been obtained indirectly from the event stream image. They're sent over here. And now the amazing thing is I'm going to get 100 frames per second video reconstruction. We've demonstrated this for pose tracking. These are actually papers that we borrowed from. But the main advantage is I'm getting a super resolution, or in terms of frame rate, image construction using a much lower energy profile over here. So this is an example of perception where you're combining two different streams. The next big idea that we're working on is to continue exploiting these additional sensor modalities. So another example of work we've recently done, and we kind of have live demos of this. This is kind of relevant to the MIT M3S project that I'll talk about. So we basically did an indoor localization for robots that are moving around. They only have a LiDAR camera, a LiDAR sensor on them. But what is happening in real time, on the ceiling are mounted a set of other LiDAR sensors with known locations. They are giving global point clouds, but from a bird's eye perspective. Whereas this LiDAR sensor is capturing things from sort of a human 3 feet above the ground perspective. So there are some challenges, if you think of SLAM approaches, it's you kind of do the registration of these two, and therefore you can recover the pose of the observer. But this doesn't work in practice because these two views are very dissimilar. So algorithms such as ICP, et cetera, fail completely. So what we end up doing is, again, for the interest of time, I'm not getting into too much details. You can read the paper, but what we do is we do one global registration, but we accelerate the computation to get an approximate location. But then as this robot is moving, we do what's called local registration between successive point clouds sensed by the robot itself. So you don't need to transfer the point cloud to the backend. It's much cheaper in terms of bandwidth demand, in terms of energy, et cetera, and you kind of estimate the trajectories. And so the end result, which I think is a pretty impressive result in crowded dynamic environments. We've done this with about 15 people moving around. We get an average translation error of 6.8 centimeters, average angular estimation error of 3.5 degrees. And the latency, this is real-time localization. We are getting the localization feed with a latency of 80 milliseconds. That's actually quite powerful using TX2-like platforms. Again, illustrating how you can optimize. And this is kind of my last technical slide, looking at the vision. So as a community, I think one of the areas we want to go after, I mentioned, stream-based sensors or neuromorphic sensors and sort of frame-based sensors. At the same time, we realize that the neural networks themselves, you have the classic DNNs or asynchronous neural networks, you have the spiking neural networks. And people have already begun working on hybrid algorithms and hybrid chips where you exploit the power of each. So one of the fallacies of the community we've been doing is we try to use only one modality. My claim, you want to combine both judiciously because each one has certain strengths and weaknesses. Anyway, this is my last sort of slide. I wanted to tell you a little bit about this M3S project. This is a new initiative just started with MIT. I am the sort of program lead in Singapore for reimagining, well, it's not reimaging, sorry, that's a typo, reimagining the future of work for various physical tasks. In particular, some of our earliest tasks are human beings working with robots at the airport in Singapore, to do things like change wheels of the plane, etc., and where the ability of the human to instruct the bot. It's a physical bot that lifts a wheel. Now it's very interesting, and as I got exposed to it, I'm actually, this is not a format where I can wait to ask questions, but I wonder if any of you know how much an aircraft wheel, a tire of a wheel weighs. And the answer is actually between 250 to 500 kgs. So you need 3 or 4 people just to change one wheel. And you can do that by using the robots for mechanical advantage, but you need the human being to point out where to tie the bolts, where to loosen, etc., and how they will work together. It's the same thing we're doing for multimodal comprehension to build chatbot-like, but chatbot, not chat, just natural interaction bot for shopping malls, it's like a concierge at hotels, etc. So this is kind of the big picture idea we're working on. And I wanted to especially mention that because this program started, it's a 5-year, 40 million, it's a very large program. And we're actually looking for PhD students, research engineers, and so on. So I'm going to conclude here because I know I'm a little bit over time. I do apologize. I actually talked about 4 different things. You can kind of read them, but let me just categorize. The big ideas: intelligent processing, which is saliency or criticality aware selective computation. The notion of collaborative inferencing, use cheaper models, but if you use hints across models, you want to do the optimized multimodal instruction comprehension. You adapt to different complexity by modifying the execution logic along different modalities. And then I talked about sort of how to bring in new modalities like LiDAR, neuromorphic video. This is not video, it's neuromorphic or event-based video streams, and combine these different types of models. So with that, I'll stop sharing because unless I stop, I can't see any of you. I hope I'm not too much over time. I want to turn it back to you.
Yeah, thank you, Professor Mr. for this nice, interesting talk. So we have probably 5 minutes. So a few questions from the audience. So I had a few questions, Professor Mishra. One of I'll just probably ask a few of them, not all. So in the context of this mosaic work, I can understand from the initial part of your discussion is that the anomaly detection is more important in many of the sensing cases. How does this method, the events that occur very rarely, fit into the kind of mosaic model, the work that you are doing?
Yeah, so the mosaic, just the description that I have talked about over here is actually more classic object detection, right? So it's not directly anomaly detection, although you can layer object anomaly over it. You look for objects that should be in places that are in places they should not be, and so on. So that's kind of an application. But I think your broader question is, can we apply the same thing not just to vision streams, but to audio streams, etc., right?
Right.
Now, we haven't quite done that work yet, but conceptually, so it's one thing to say I've done it for audio streams. I haven't. But I think the concept that applies is that you are doing some very early feature extraction even from the audio stream. Maybe you sample, you don't do a full Fourier transform, but you do a time domain transformation to extract a few high-level audio features. Then you combine all of these composite audio features, maybe by doing frequency offsetting, which is easy to do with a mixer. Then you run it through an audio-based DNN, which will help you isolate which streams have something of interest, because you have combined all of the streams into one single audio stream by maybe shifting things in frequency. Now, once you do that and you identify which streams have interest, then you can sort of do a closed loop feedback. Then you say that in future, I want to devote more of my sort of frequency transformations or feature extraction to that particular stream in real time. So that, I hope that gives you a sense of what the analog of the vision-based work might be for like an audio stream.
Right. Thank you. I have another question from your POM AI work. One in that work, since there is a multiple cameras looking at the same scene, and your region of interest should agree on these different camera views, right? Otherwise, this method might not work. For example, the example that you have given, two people walking side by side. And if these two cameras region of interest does not agree, then this method will not work. Is that my understanding correct?
Yeah, so great. I think that's a very good question. So implicit in this is that there is a previous step. In the example I gave you, there is a previous sort of, if you call it a calibration step, where the two cameras, we have identified what is the overlapping field of area, the physical area that they can both sense, which is the overlapping subregion, and they know how to transform from one pixel coordinates to the other, right? Now, you can do that through a variety of different mechanisms. If you know the intrinsic parameters, etc., you can do, but probably less. I mean, there's a set of vision techniques. But yes, that is an assumption, and that only works if the cameras actually have overlap. But what I did not talk about, the same idea works, not in the spatial domain, but works in the temporal domain. So take the example that you have a camera in the lift, and then you have a camera next to your lab space. And you know that somebody coming out of the lift will reach the lab space somewhere between, say, 8 to 15 seconds. Because not everybody's going to walk at the same speed, right? Now, what you do over there is you actually transfer the features detected by the elevator camera to the camera in front of your lab door, and you prime it to say that I expect you to see somebody with these features 8 to 15 seconds now. So then you can look for these features to reinforce if you're getting this person. So the same concept can work without spatial overlap, but it's basically exploiting that there is some correlation, either in space or in time. Sorry, are there any other questions from anybody?
So there is a question in the chat. So just read it out. Is it possible to determine the ideal bounding box size by applying any bi-objective optimization in the data set?
Yes, certainly. I think there is a variety of different, so the main point is what is the objective criteria? What is the objective criteria over here? So in terms of determining the right bounding box size, you want, it's not so trivial to say that there is a bi-objective, because remember, it's not just a function of the size of the objects, but it's also sometimes related to how the objects are clustered together. Because one small object here and a large object here will lead to a different tiling choice than if these two are together. Because if these two are together, you want a bigger tile to capture both of them. If they're far apart, you need a small tile here, you need a larger tile here. So this concept, yes, you can do bi-objective optimization, but you also need, if you really want to get very sophisticated, you have to incorporate the spatial relationships between the objects in real time. Now, the reason we didn't do that, or variants of that specific approach, is that we are running a real-time system, and all of these additional sort of parameter selection methods consume tens of milliseconds of latency, and that sort of slows down the overall pipeline. So that isn't so much a computational intelligence question, but it's kind of a systems optimization perspective, where you look at the end-to-end latency and you see which parts you can minimize. I hope I've answered that question.
Yeah, I think so. Let us thank Professor Mishra for this interesting talk, and thank you, Professor Mishra.
Certainly, my pleasure. Thank you very much for having me.
Yeah, so we can move to the next session, please.
Yeah, thank you, Professor Archan Mishra, Singapore Management University, and Dr. Himadri Pal for this session, for this insightful and interactive session. Moving forward to the second lecture entitled Clothing Dynamics on 3D People by Dr. Rajeswar Bhaumik. He is from TCS Research. To do the chair of this session, may I invite Professor Siddhartha Bhattacharya from IEEE CIS Kolkata. He is the current chairman of this chapter society. Let me introduce Professor Siddhartha Bhattacharya, and we'll start the next session. Dr. Siddhartha Bhattacharya is an accomplished academic with a diverse background. He holds a bachelor in physics, bachelor and masters in optics, and from University of Calcutta, India, and a PhD in computer science and engineering from Jadavpur University. He has received various prestigious awards and honors, including the University Gold Medal, Distinguished HOD Award, Distinguished Professor Award, Honorary Doctorate Award, ICT Educator of the Award. Throughout his career, he has held significant positions in academia, including serving professor and head of the department at various institutions. He has co-authored numerous books, research publications, and holds several patents. His research interests span across hybrid intelligence, pattern recognition, multimedia data processing, social networks, and quantum computing. Dr. Bhattacharya is a fellow and member of several renowned professional societies, and served as an editor and series editor of various international journals and book series. He has been actively involved in organizing and chairing numerous international conferences and associations related to artificial intelligence and computational intelligence. He is currently holding the position of principal at Rajnagar Mahavidyalaya, Rajnagar, Birbhum, and serves as a scientific advisor of Algebra University College, Croatia. Additionally, he has been associated with other esteemed institutions worldwide, contributing significantly to the field of computer science and engineering. So, may I now like to invite Professor Bhattacharya to chair the session. Over to you, sir.
Thank you, Somnath, for your nice introduction. In fact, it was a very good session, the previous one, the first one. So, in tune with that, let us now start the second one with Dr. Rajeswar Bhaumik to deliver a talk on this clothing dynamics on 3D people. So, before starting the session, I'd like to just have a quick introduction of Dr. Rajeswar Bhaumik. Dr. Bhaumik is a principal scientist leading the research in the area of visual computing and embodied intelligence in TCS Research, Kolkata, India. He did his PhD from the Department of Computer Science and Engineering in Indian Institute of Technology, Delhi, in the areas of computer vision. And he also did his BTech in Computer Science and Engineering from the University of Kolkata. He is a fellow of the IEEE, senior member of IEEE, and associate editor of Springer Essentials Journal. He has served as an organizing committee member and program committee member of several international conferences like ISBI, ICVGIP, CBPR, AAAI, IJCAI, WSCV, ICLR, etc. He is a recipient of the Best Paper Award in ICVGIP 2018 and 2021, Best Demo Award at ICDN 2020, Patent Champion Award at TCS Research in 2016, and Special Mention Young IT Professional Award by Computer Society of India in 2008. Dr. Bhomik has published over 60 research papers in the areas of computer vision, graphics, artificial intelligence, and robotics, and has more than 30 granted patents. With a small introduction, I would like to invite Dr. Bhomik to come up and then deliver his talk on clothing dynamics on 3D paper. Over to you, Dr. Bhomik.
Thank you, Dr. Siddhartha. Hello, everyone. It's going to be late night, so I'll in Kolkata. So I'll start very soon and be very brief. Let me share my screen and let me know if my screen is visible.
Yes, it is visible. You can go carry on.
Okay. Okay. So yeah. Hello, everyone again. So the topic of today's discussion is clothing dynamics on 3D people. Some of the animations and the output that you are seeing in this particular screen, hope you'll be able to understand what I'm trying to say. But still, I'm motivating with an example. Suppose we have RGB frames of a person doing something, right? And it's monocular, means it's captured from a single camera. Now, what we can do is that we can estimate the person's pose, shapes, and everything. Obviously, hairs and others are very difficult to do, but I'm restricting myself to the clothes at this point of time. And if we can do this, then we can have a model which takes the clothes from a wardrobe. So these are the 3D garments. And I'm assuming that those 3D garments are available, but generating those 3D garments is an additional problem. But right now, let's assume that these are available. And if I get that as an input in the draper engine, it should be able to drape that particular person of that particular shape and produce all those wrinkles and everything which is induced by those motions. Now, when we have to make this realistic, we have to do the appearance transfer of the persons and project that into 2D and all, 2D and all these hair stuff will be there. But getting this geometry and wrinkles, animations, conditioned on the human pose and shape is very important. So why we are doing this? Because you know that in all these retailers, they need this product cataloging time to time, right? So it has a series of steps, like you contact a photographer, the shortlist of fashion models, they will appear in front of the photographer and wear those garments, and you have to do the photo shoot and editing, and it's hugely costly manual process. So that can be minimized to some extent if we can automate some part of this process, at least the shape and pose that we can automate, then rest of the things at least can be photoshopped or can be used editing tools, which will save some time and with a huge amount of time. The applications will be, another application will be garment try-on. You would like to see yourself while buying a garment for yourself over online e-commerce. Dressing characters in video games, which is obviously needed. Nowadays, video games characters are also has to be very realistic, otherwise kids don't play. Fashion show and showrooms, these also can be a virtual, you don't need a real model. And you can have a AR glasses or any kind of VR platforms where the models can work and you can see those garments animating based on the work. So there are many such applications if we are able to automate some of the processes. Now, in this particular talk, I'll show what are the things that we are doing and where the state of the art is and what are the problems that needs to be solved. But before we go into that, I would like to say, what is this chat, this dancing 3D model? What is this? This is called SMPL body model. It is a statistical 3D body model, but governed by broadly two set of parameters. One is shape and is pose. The shape is a fixed length vector, is a shape vector, whose values could be interpreted as an amount of overall body fatness or weight. So is a vector, and it is represented as a mathematical entity which can scale or shrink to create new body shapes based on height or weight, right? So how to create that? So there are many sophisticated engines, machines or cameras, which can scan our body from different angles. And if many people are scanning themselves, then we are going to get several of such scans. And those scans are getting registered into a template. All the holes that are going to get in the scans, they are going to be completed. And then we are going to get many such scans of different persons having different shapes and different body weights, different heights. Then one option is that one can do a principal component analysis. Traditional face recognition engines also use that, and create a digital representation. The eigenvectors are also becomes the human body, but now the eigenvectors are principal human body shapes, which can be altered through the eigenvalues. So if you have these principal vectors, I hope my full screen is visible because I'm seeing the window also here. If you see the eigenvectors that are being computed out of this principal component analysis, and if you multiply them with some floating point numbers, like you are doing these eigenvectors, eigenspace manipulations in linear algebra, you are going to get a new body shape, a new body, right? So this is about shape. Now, what is pose? Pose is also a similar fixed length 24x3 scalar values, which is about the rotation of each joint with respect to the root or the parent joints. And this is a three-dimensional rotation matrix, which is a relative rotation between joints and the global orientation. So if you see this particular figure, you are seeing that the white dots here over the body, they form the skeleton, which is shown in the right. And this theta is denoted globally as a pose vector, which is a 24x3 scalar values. And these white joints are estimated based on the body semantics. Whenever the SMPL is computed, the body semantics is known, means which part is a hand, which part is a leg, and based on that, it computes the underneath skeletons, and which can be used for maintaining different poses. So now this is a digital representation of a human body. Now, if I give a summary, which we have just now told, so we have a template mesh in a rest pose. These are the joint location. Now, if you have a blend shape, if we change those blend shape coefficient, we are going to get different shapes of the body. And when we are changing these shapes based on the blend shape coefficients, we can also do the same thing based on pose blend shape. Means whenever we are creating some poses over the body, you see some of the muscles in the third GIF, third human body, is getting changed due to the fourth pose, fourth GIF. That means that whenever your muscle is floating or shrinking, your shapes are also getting changed locally. That's because of the skinning or muscles of the human body. So this is a very good representation which one can use to compute the human pose analytically. Now we know that what is this human pose and how what is this human body model which we can use. And the question is how to compute this from an image. So we know that this is a parametric human model which can be altered based on certain coefficients, but we need to alter those based on the RGB. There are many works on this particular topic. We are not the one that we are doing first. Now, this is an example what I mean by recovering the 3D body pose and shape from monopolar images. So you are doing some genes or some actions over body, and your SMPL body model is getting fitted there. There is a popular method, just CVPR 2022 method, which tries to understand how to make these estimations temporally consistent. So they try to find out which part of an image, means which image in an image sequence is correlated to another image in the same sequence. So if I take a very longer sequence, then the correlation between a particular pose in an image tends to be uncorrelated with the further image. So this relationship, the temporal relationship, can be encoded as an attention vectors among themselves and try to discover those attentions through neural network automatically, just to make them temporally consistent. And we know that we are working on SMPL body motion. So we generally have a backbone of image features. So you pass on to the VGG or ResNet model, try to get them the feature vectors, and the attention is computed between those feature vectors. Try to understand how long I can stretch for a particular image in a sequence to validate whether the sequence at the 10th image in my list is correlated with the image that in my hand or not. Obviously, in a video sequence, I'm talking, and these are 10 image window. If it is connected, if it is correlated, then that information is passed on a second stage, which is trying to get the temporal features out of it through those attention, and then it is getting regression over the theta. The theta means the poses that I was saying, and it is getting projected back to the camera, and you have the silhouette. You are getting correlation. So this is the technical diagram of the attentions and the self similarity. And there is also involvement of the camera, because the camera can be dynamic. So the camera estimation is also part of the process. So if you estimate the camera and you estimate the attention model for a particular image, you are going to get them both together. And this camera estimations is going to be useful for projecting the 3D estimations back to the image and get the correlation. So this is a video, this is a video of that particular CVPR 2022 paper, which you can see that this is a very nice fitting of persons walking and doing some activities. Now, if I go next, when there is a pose ambiguity, you see that this is a pose ambiguity. Now, you notice this video very carefully. You'll see that it got flipped suddenly, although the person has not flipped, right? So these are the problems of the existing algorithms. When there is an occlusion, you see the fitting is not correct. So the legs is not correct. In the left, the estimations have not happened at all. If I vary the lighting condition, then you see this fitting is not accurate and many frames are missed. So these are all problems in practice, and this is a very recent method, and this is a very difficult problem to solve. And if we make this human complex motion, then you see that it doesn't work at all, right? Now, if you make it much more complicated, like severe occlusion or something, like partial body or occlusion, then it miserably fails. So these are the situations where, despite of this temporal continuity, this feature mapping and everything, is not having accurate results. Now, this paper is submission. Therefore, I'm not revealing the core technology, but I'm saying what we have done in this particular space recently, very recently. So we have also have these input video sequences, and we have this per frame initial estimations. So there are methods like PARE or PARE-like methods. PARE is a method proposed by some other authors in ICCB 2021, maybe. So we can have any method which is reliable one for per frame initial estimation. And what we have, a body aware feature extractor. That body aware feature extractor, usage of this body aware feature extractor is our novelty, which I'm not going to detail in here, but it's kind of, you can say that this is a local body attention map, which says that which part of the body is much more visible compared to the other part of the body. You can say that's a part-based model. And also we have the body aware spatial features, which is basically connecting one body semantics to other body semantics, like hand with torso, right? Or shoulder with torso, head with your neck. So this is a body feature, spatial features that we have passed on to the self-similarity and the attention map. And then we are going to give, we have done spatio-temporal feature aggregation, followed by a refinement using LSTM. So this is the high-level architecture. I'm not going to details into the low-level, very design-level architectures. But this is what the what we did. primarily using the power frame estimations, body aware semantics extractor, spatial features extractor, and camera pose to get the spatiotemporal aggregation using the same self-similarity and attention. With this, all the problems that I mentioned earlier that get somehow alleviated. You see in the right, you have seen this flipping problem, which is not there in our method on the same cases. In the pose ambiguities case, the occlusions that we showed in our method in the middle, you see that the poses are much more legitimate. At least we are able to estimate how it should be. And in the severe occlusions, MPS net was not able to do anything. Our leg most portions are coming out quite well. In the lighting condition also, in the zoomed in version, you are seeing that our estimation in the slow movement, you see that estimations are more correct than the MPS net. And if I go further, you see complex human motions, which I showed earlier. Our method is much more reliable than what we have seen, and also in the severe occlusion case, even if the body is partially or fully occluded, our method will be able to predict much more temporally consistently. So this is about the left part of the things where we are able to estimate the 3D human temporally consistent. But now come to the next stage. Given this 3D human estimation and digital wardrobe, how we can animate this garment and drape it. So for that, we need to have important observations how to represent a garment in a computer. Now, cloth is a continuous material, but we work on a digital computer, so we have to have a discrete version of it. So one way to generate the geometry is by using triangles. So triangle is made of 3 vertices, and you can say those vertices are particles, and they are connected by edges. So you see in the left one is a cloth picture by a photographer, and the right one is a digital version of it, where you see that triangles are there to the entire clothes, and this is a digital replica of the true clothes. Now coming to the deformation, how to deform it. For that we need certain background. I'm going to give very brief this particle physics background, which we'll be using in our context to drape or animate the garment. Now I told that the garment is consisting of several triangles, and triangle has 3 vertices. We can say that these are 3 positions, and every vertices has their own velocity. So this velocity is important because whenever we are deforming the garment, the vertices are getting changed over time, and therefore there is a velocity associated with it. This is obvious, right? Now, if we have all the vertices of the garment, if we take them together, we can create a vector of positions and a vector of velocities. This is just a vectorized form of the entire garment. If you have that, then we know that velocity is a time derivative, the position defined between 2 positions with respect to time, and acceleration is the velocity difference. That's a normal motion equation. And if we use that in a linearized form, then we are going to get this xt plus 1, xt plus h equal to xt plus h into vt. Obviously, this is true if the h is small. And if I use the forces into it, and the Newton law of force, then this F equal to m into A, and this force can be internal forces like internal deformations of clothes, of stretching, compression, shearing, bending. So all those forces which are responsible for displacement of the vertices can be contained in the internal forces. And the external forces can be gravity, collisions, aerodynamic effects such as wind or something, which are also forces are responsible for displacement or inducing the velocity of the particles. Now, if I use this force into the equation, then the velocity becomes h into m inverse of f. Now the acceleration is replaced with mass and force, and these particular formulations, that the way I've written is of interest, because there we are not explicitly dealing with accelerations, but we are dealing with force, and we can define the force based on this internal and external in the computational world and manipulate the vertices. That's the main idea. So this particular formulation, this xn plus 1 equal to xn plus h into vn, and vn plus 1 equal to vn plus h into m inverse fn, this kind of integration is called forward Euler integration. I hope many of you know this. Now coming to the different kind of forces which are going to induce a deformation. So we know that from classical physics, force is represented as a negative differential of our energy potential, right? Now I'm given here a small mesh where there are few colors edges, this red, orange, and green. So these are all identified as the edges which are responsible for creating different kind of forces. In the right, you are seeing the stress forces, shear forces, bend forces. Now let's take an example of stress forces. Stress forces means the forces which are making these triangles or the regions elongated. You see the stress forces are being applied on the spring. So these edges are denoted as a spring. If you see the green lines and imagine that the stress force is applied there, then the vertices are going to be elongated over the horizontal or vertical direction, right? That's how the spring is attached. So those springs are only responsible for stress forces. For shear forces, we have a different set of strings, and for bend forces, we have a string which is one hop connection. So from I to I plus 2 connections, because if those strings are getting contracted or expanded, then the bendings are going to happen. So this is implicit formulations based on the string theory, how we can induce the forces on a mesh, on a digital structure. And if we can control those energies, those forces will be acting based on this differential, and this kind of deformations we are going to get. Now the challenge is that can we retrieve those forces from the video or based on the body and try to animate? That's the main idea. So I'm now describing what are the different forces and what are the formulations that are possible. One is gravitational force. Force is a negative potential of energy. So X and Y doesn't have anything. So the gravitational force is under Z direction. I'm just assuming Z is my vertical direction. So it becomes minus mg. If I take the gradient of it, it becomes minus mg, which is easy. Coming to potential energy based on this spring thing, we have this potential energy of a spring, which is from physics. I guess everyone knows. Now, if I take this derivative similar to this same equation, I'm going to get this, the third equation. Right. So this is what the force, that this is a function of position. So if I give this force to the system and I try to manipulate the displacement based on this particular force, I can get it because I know this force and I know the Euler forward integrations that are dependent on the force. I can get the next step based on the previous equation that I showed. Similarly, I have a damping force because whatever the force that we are inducing on the garment, that because of the gravity or because of the body, that has to be dampened. Otherwise, it will keep on exploding, which is not a very good behavior. So the damping force is also based on the spring theory, and it is also a negative coefficient of kd into more this difference of the velocity of two vertices connecting the edges, the more the damping will. Stress force, which is important force. Now this requires a bit of understanding that the coordinate of every vertices are in 3D. So we have x, y, z, but the triangle is in 2D. Just hear me out. The coordinate of every vertices of the triangle is in 3D, x, y, z. But if you take the coordinate on the triangle, then triangle is a plane. So every vertices of the triangle in the triangle coordinate systems are in 2D. So there is a map from 3D to 2D, and we can try to find out for a small displacement in 2D, how much that is their displacement in 3D. So that is called the stretch gradient is W. You see WU and WV. That means WU is the gradient of X with respect to the deformation in U. U is the coordinate system on the plane, and X is the coordinate system in 3D. So if I make a delta change in the triangle coordinate system on a vertices, what is its impact on its 3D? So this makes a stress force, and this particular equation, I hope my cursor is also visible. This particular equation where C is mentioned, Cx equal to Cux and Cvx, is called a conditioning of the system. And this conditioning of the systems is going to be defining the energy of the system. And B is 1. So ideally the gradient should be 1. That means there is no change. More the change, more it is going to be divided from 1, more the stretch is. So the Cx is defining implicitly how much a triangle is stretched in by a particular direction. And the Cx transpose Cx is defining the total energy that needed to overcome the stress. And because this is an equation in a closed form, we can derive this differential again and formulate the stress in a closed form equation. Shear is also the same thing. We are using the same conditioning like these WU and WV. That means how much in the 2D coordinate systems that we are changing the coordinate and how much it is going to impact in the 3D. Right. The same we are doing in shear in a particular dimension, in an in-plane shear. Finally, the bending force. This bending force here is characterized by the angle between these two triangles. So if I have a normal, if you say every triangle has a surface normal, that means if your triangle is a plane, if you take two edges of a particular triangle, take a cross product of them, and you are going to get a normal output. So is a orthogonal to the plane. And if you have two such normal for the two adjacent plane, and if you get the angle between them, then you are going to get an estimate of a bending of two triangles, two adjacent triangles. So if there is a bending in the garment, then it's not good, right? So you have to estimate that as well. So these are the example forces. There are many forces which we can devise and we can use to deform a particular triangle or a set of triangle. And if you are able to deform a triangle or a set of triangle based on these forces, then obviously automatically it induced to the vortex displacement. And if there is a vortex displacement, you are going to get animations over the clothes. Now coming to the optimization process is physics-based simulation. So we know that forward Euler integrations that I told you earlier is about del x equal to h into Vtx and del v equal to h into m inverse the forces. And how the integration happens is the addition of the deltas with respect to the time steps. Now there's a concept of backward Euler integrations. So what it does is that while the forward Euler is predicting the estimates based on the previous estimates and the delta produced by the forces, the backward Eulers, the forces are also taking care of the future parameters. You see in the previous equation, f is a function of xn. And in the backward Euler, the f is a function of xn plus delta x. I'll come to in the next slide what is the benefit of it. But it says that before you are estimating the next state, you are having a extrapolation of the function force of in the next state, and based on the extrapolations, you are computing the previous state's value. Right. Now, because this is the delta x is both sides, so it's a nonlinear one. So we can make it linearize based on the Taylor expansions, which with all higher order terms are neglected. And then we rearrange this particular term with respect to del x and del v, taking the del v in the and del x in the left side and everything in the right side. Then we are going to get closed form solutions like a into v equal to b is a linear equation, and we can solve for b, right? And this becomes a complicated matrix you can imagine, because it has all these forces, derivatives, and x derivatives. But if the forces are defined analytically, then these derivatives are also analytical. You have a closed form solutions, and those closed form solutions can be put into algebraic form in the A, and these linearizations can be made, right? So what is this comparison? The forward Euler takes no notice and proceed with the integration blindly, right? So xn plus 1 is taking the xn plus delta x, and delta is only dependent on xn. It has no idea how these derivatives are going to behave, how the force is going to be behave with respect to x or v. But the backward Euler is taking care of that forces on the output state, whose derivative at least point back from where it came from. So it knows that the next state that I am going to be estimating, what will be the force there in future, depending upon the force in the previous state. So what is this advantage? It makes the system stable. How? Let's assume a simple differential equation, which dy dt equal to ft yt with a boundary condition y is 0 equal to y at 0 times step equal to y0. And let's assume that the f that we are talking about is lambda into yt. Is a simple differential equation. Now, if we go for the forward equation, forward solving, then we know that yk plus 1 will become yk plus h into ftk yk. That's the forward Euler integrations that I have outlined in the previous slide. Now, ftk yk I have parameterized by lambda into yt. So that is going to be replaced by lambda into yk. And if I make it altogether by taking the common yk, then it's become 1 plus h lambda into yk. Now, if I do these integrations over time, then I'm seeing that 1 plus h lambda to the power k is coming into a factor. And if k 1 plus h to h lambda is greater than 1, then yk is exploding from y0, right? But the real world phenomena doesn't have automatic injection of the energy to grow infinite over time, right? So this is not a correct. There's no damping. You need to have a explicit damping in these particular formulations to grow it exponential. And this curve show that this the red timestamp in the left red point. If you are taking a tangent, in the next timestamp you are reaching to the tangent which is beyond the curve, because you don't know what will be the next estimation that is possible, right? The tangent that is possible. Now, see the backward thing, what happens there. So in the backward thing, we have yk plus 1 equal to yk plus h f of tk plus 1. Remember, this is a time step of k plus 1 instead of k, and yk plus 1. Now we are doing the same thing, yk plus h into lambda into yk plus 1, because f is parameterized by that. Now this yk plus 1 becomes in the left side, so 1 minus h lambda into yk plus 1 equal to yk. And yk plus 1 now becomes with the entity which has fraction 1 by 1 minus h limit to yk. Now this clearly has to be less than 1 for a positive time step, and it is there is an implicit damping, and it's unconditionally stable. So there is no explosions happen. And in the figure also you are seeing that there's a tangent in the future time step of the force of that particular curve, and we are using that particular tangent to find out the tangent means we know the angle, so we are basically forwarding with that particular angle. We are not correctly estimating, but we are not overestimating, right? So at least there is an implicit damping. Now this particular implicit backward integrations with the forces can lead to large step. Because why I'm saying large step? Because you see that this particular k can be anything, still it is damped, right? So you can go for last step, but in the forward you have to have very minute step, because h has to be very, very small, right? So this is the first work that is done on the SIGGRAPH 1998, where the authors of this particular paper showed how to use that particular optimal animation strategy to deform a garment. So the algorithm goes like this: that if you generate an initial planar triangular mesh, the way I told you how to represent the garment, or define the UV coordinate over the plane and XYZ coordinate over all the vertices. Define the initial velocity of all the vertices, definition of mass of all the vertices. You can compute them because the garment is in the static, so you know the gravity is in the lower directions, and you can initial velocity can be 0. You define the stress and shear coefficient for all the triangles. So the way I told you that explicit formula exists, and define the bend coefficients also, so that triangles doesn't break. And then for every loop of the triangles, compute the stretch and wear forces between 3 vertices. For pair of triangles, compute the bend. And for all the external forces, you compute the gravity. And then apply the implicit integration. Right. So once the implicit integrations are done, then you are going to get the displacement, because you are going to get the xn plus 1 and vn plus 1 given the nth estimates. And you are going to get the deformation of the garment vertices over your body. So this is a demo. You are seeing this is a marvelous software which use this kind of physics-based simulations on a body. I'm just skipping this video just to show you how it is done. So this is a simulation that is happening, and all this stuff that I just now told is being run in the background, and it is getting optimized. So you see that once the garment is draped on a particular body, you are just hanging it over, and now you are free flowing, and you are going to give it optimization. Slowly, if you see that this is deforming, but this deformation is very slow. It is aligning with the body, right? Now this particular process has some demerits. They are very computationally costly, because it needs a set of so many triangles. If the resolution is very high, you have to compute all these vertices, all these forces, all these gravities. And there are manual interventions. You have to drape the garment over the body, and you have to do the tough alignment like the way this software is doing. And then all these matrix inversions and everything needs to be done to make this happen. But this works. And it's on 1998, which seems to be very good. But nowadays, people are moving to neural network, because neural network has universal function approximator, and it does very well in optimization. It has an autograd facility. All the gradients that I'm saying, that can be estimated using our autograd functionalities that I'm going to show. So people have moved to the neural network domain and trying to do the same thing in that domain. So there we have a couple of works. Two or three publications in this particular domain. I'm just selecting one which is published this year, WSCB. I'll describe in brief what we have done there. So setting is this: we have a canonical body pose, and we have a 3D garment. Now we know that we can record these motions from the images, but right now we are taking these motion captures motions of the human body and try to animate it. Now, our target is we should train a single model which can handle arbitrary types of garment, varying fabrics like leather, silk, cotton, different topology, right? Like full skirt, or full t-shirt, half t-shirt, and arbitrary body shape and poses. All these are variable to us, and that will be all these will be handled in a single network. And this is what is not existing till we published our paper. Now there is one more paper come out using the same philosophy in CVPR. I'll show that also. But till CVPR 2023, in WSCP 2023, there is no such state of that. So we are the first which proposed this. So the underlying principle of this is that we have this canonical body pose, we have this template garment, and we have the target body pose. These three we have as our input. Our job is to design a neural network which is physics-based, because we'd like to estimate the forces, we'd like to estimate the velocities, accelerations, and our garment is a mesh. We'd like to retain that property of the mesh as it is without doing any embeddings, the explicit embeddings. And the better way to represent the garment in the computational framework is to use graph. So we have used the graph as a representation for the mesh, and we have developed a physics-based neural network which tries to produce the dynamics of the garment conditioned on the underlying body motion. So the only constraint that the garment is having is the body motion. Okay, so I'll give you a brief methodology how we did it. So we have this template garment, we have this SMPL body pose. Now you remember that I showed you this pose. If I have a skeleton pose, I can induce that over the SMPL body, which is a mesh. How do I do this? It's called skinning. Skinning means every coordinate in the skeleton pose, every coordinate in the skeleton pose has a mapping to the skinning vertices of the mesh. Mesh has this particular right side, mesh has an XYZ coordinate. Skeleton underneath the mesh also has a XYZ coordinate. Now the relationship is that for a particular coordinate in the XYZ of a skeleton, there is a relationship with a set of neighborhood mesh vertices, and that called linear blend skinning. So when we are deforming our skeleton, our mesh that encompasses the skeleton are also getting deformed based on a certain set of vectors, which is predefined for a human body. So the skinning coefficients, we call that linear blend skinning coefficients. The skinning coefficients that are responsible for deforming the human body mesh based on skeleton, we can use that also to approximately change the garment. Although that change is not good, but at least it will give template deformations based on the target pose. If you see in the left that there is a very smooth, nice garment, and in the right you are seeing that the different views that the garment is getting deformed, but deformation is not good. And our neural network job is to correct the deformation as much as possible. Remind that there are a few artifacts which you can see, but these artifacts are no more there today. We have improvised this method, but this is the first method we showed that this is possible for arbitrary garments without retraining any other neural network for garment specific. Most of the state of the art works on the retraining process. So they retrain the neural network every time as and when the new garment comes. Okay, so now what is the pipeline that we have followed? So we have the input garment graph, we have the template garment, we have the canonical body pose, and a target body pose. The canonical body pose in the T shape, and we have the target body pose. So we started doing encoding of the garment geometry encoder from the template garment, underlying body geometry encoder for the body, and the body semantic encoder from the semantic part of the body where the garment is going to influence the body, right? With these particular three things, we are creating high-level encoding, which are basically garment feature encoder and body-aware feature encoder. The body-aware feature encoder is based on this body semantic encoder and body geometry encoder, and the garment-aware feature encoder is solely based on the garment encoder. And these are the node features, and we also have the edge features, which are describing how much the difference between the edges after deformations and before deformations. So in the right, you are seeing that PI is the garment template minus the body nearest vertices of the garment. And we have the prior for this also. Prior means after the LBS deformations, and edges are the difference between the two garment vertices, and similar for the prior. So our job is to take these as a variable and try to produce the displacement and the magnitude of the displacement from the neural network. So when we have computed these estimations for each of the node features and the edge features, we have to propagate the node features and the edge features across the neighborhood node. It's called message passing. Why this message passing is required? Because we think that the force induced at a particle should get propagated to its near about particles, because the force should also get influenced by the others. And this message passing is starting from the neighborhood vertices to the neighborhood nodes. And when the nodes are getting updated, with each updated features in the node, we are updating the edges also. So edges features and node features are simultaneously updated one after another based on this message passing mechanism. And then we are producing the velocity and the direction of each particles of the mesh vertices and try to produce a deformation based on the underlying body condition. So this is the output of the final garment, which we are predicting. And in the right, you are seeing that how much the garment, the more the color is, the more the deformation is. So how much the garment has deformed from its template positions. So these are the losses that we have used. First loss is how good the prediction is. So we have a ground truth data using the physics-based simulations that I just spoke. We also have these smoothing loss, like this Laplacians, which I spoke also, that so that the garment should not bend much. And we also have the penalty losses, body collision penalty, so that garment is not penetrating the body. So it should not go inside the body. These are few results which shows that our Garsim method is having very low collision and a very good amount of Euclidean error and normal consistency across different subject and different garments. So this is the state of the art at that point of time. We compared with the most recent state of the art, deep PhD and other garment specific methods. So these are animations that shows that how this method is performing on different garments with different complex motions in running, walking, and upside down animations and everything. So this is quite stable, and you see that it is following the underlying body motions quite well. These are few other deep draper, deep PhD, PBNS, the state of the art against which we have compared our method, and it clearly shows that Garsim behaves pretty well than the other methods which are trying to drape 3D printing. And this shows that our method is also fabric aware because it shows different kind of deformations on different kind of fabric. So leather, the deformation is pretty less because it is much more rigid than the silk. The silk you see is much closer to the body. So this is the distance from the body, this millimeter. So the leather is far from the body and the silk is near the body. That means the deformations for a single garment is following the fabric property. These are the few generalization output that we took the YouTube videos. We compute the body poses based on the human motion capture that I described earlier, and try to use our method to drape different kind of scarves or garments on top of that. Now the problem is that this method is dependent on data because we have used a ground truth to regularize it, as I mentioned. Message passing of force are limited to a limited neighborhood, but is not good for defined fabric because defined fabric has defined kind of message passing. And we are not utilizing the implicit integrations, which I told that in physics-based simulation, implicit integration is a good idea. Now, all these limitations that I just now spoke is being solved in CIPA 2023, which tries to model the garment in the pretty similar way that we did. They model this garment as a graph, and they just not model the as a one resolution graph. They model these as a multi-resolution graph. So they have high resolution and low resolution both, and they do the message passing like the way we do message passing. The only difference is that they do message passing at a hierarchical level. So the coastal level messages are passed to the final level also in the edges and then the vertices. And then they do the predicted acceleration like the way we do. And we are doing frame by frame operations, and they are doing the auto-regressive for 5 frames at a time. And then they are producing these results. And the similar results that we have also shown in the last slide. But the main intrinsic property that they have used is the backward Euler, which I showed you that the backward Euler is trying to produce the forces based on the next time step. So if you take this equation as a force equation like the previously, we showed that m into f acceleration is the force, and if I take everything together, then I can devise the optimization systems with a variable with a function h, where this m into I've written the v as a function of x, or v as in the form of x, because velocity is a function of a position. So I've just done the algebraic manipulations here to replace the velocity with the position and putting the f in the left hand side and making the entire objective as a function of h, xn plus 1. So our objective is to minimize the equation so that we are going to get a correct forces and corresponding correct position estimation. Now to do that, let's phi be the potential function replacing the f in our case, because f are the forces. Let phi be the forces now, and we are adding that phi here as a function of h, because this minus f is becoming the del phi del x, because we know that f is a differential of energy, right? So phi is potential function, and we are denoting f as a del E del x. That means del phi del x, and this minus become plus because force is a negative potential. So algebraically this is correct. Now we need to define this as an energy. Now what we are doing is that we are forming reparameterization of xn and xn plus vn into t delta t as a x hat. This is just a reparameterization of what is written here in the previous equation, the right side of the equation after xn plus 1. And we form this particular energy in a quadratic form. And notice that if I take this derivative of this energy, it becomes a solution of hn plus 1. There's a trick that they have used. So this quadratic energy that they have formulated algebraically, if you take the differential of it, it becomes the solution of xn plus 1. Now, because and in our case, xn plus 1 has to be 0. That means that del E del x has to be 0, which is easy to get in the today's PyTorch autograde, because autograde is going to minimize the energy if I formulate this particular energy in the neural network paradigm. This precisely they have done. So they have used the linear blend cleaning as an optimization for as we did in the WSCB. Now they solved this particular function, these energy functions, to further minimize it, to make the initialization even more better. And then they devise all these forces, like the way you also devise the forces, the inertia forces, the same forces that I described previously: bending force, gravity force, stretching force, collisions, and frictions. So all these forces that they have devised and inherited from a CPPR 2022 paper and try to optimize them in the automatic gradient descent way. And these are results that they have produced. If you notice that these results are quite appealing, and they are following the body structures as we are also doing. And this is a second paper after we published, which also take care of all the properties like the fabrics and defined topologies, defined body shapes, and everything into account on a single model. These two are the today's state of the art that are possible. One is from us, and this is from Max Planck University. Okay, so still there are few problems which are open and we need to solve as a community. One is the garment self-collision, and one can design a repulsive force while deformation is happening so that the two garment vertices are not colliding each other and penetrating each other. Layered garment, right now I am just showing you one single garment over body. So if I have multiple garments over body, that also need to be animated. There exists a bias in the human motion in the training data, because all these human motions that I am showing, that human motions are from the motion capture system. So motion capture system has its own bias. So we have to get rid of that in practical sense. This particular paper also has computed the body to garment correlation. So which part of the body is correlated with which part of the garment. So if that goes wrong, then the garment deformation condition on the underlying body is also going to get wrong. This is also a problem which our method and the CVPA 2023 method both are having, so we need to solve that also. The explicit modeling of particle interaction as a graph is a significant computational overhead, because we are saying that every edge is going to be part of based on the node positions which the edge is holding. And for a high density graph, dealing with every edge is a very difficult problem when the nodes are very high. So we need to have a handler efficiently to minimize that computation so that the animations are more or less real time. So these are all the problems that are yet to be solved, and I guess community is working, we are also working. And if some of you are interested working in this kind of areas, you are welcome to contact me as your thesis or pre-doc or postdoc or any other capacities in TCS research. So with that, I'd like to conclude my talk. If there is any questions, I don't know. I guess I hope I'm within my time. I'll be happy to take those questions.
Thank you, Dr. Bhomik, for your very excellent speech. A new field altogether to us, having understanding the different aspects of garment modeling and all these things, which are very typical tasks for some typical applications. So I'm now I'll ask to our audience if they have any question, they can just come up and have their questions answered, or can just put a question in that chat box.
I have a question on this work. How this compare with the new diffusion model like Dell E, version 2, from text to video generation, text to all kinds of things. There was a movie, I think Frost, 12 minutes movie. The entire thing is generated by this kind of generative AI. Is that comparable, or they're two different beasts?
Yeah, so it's a good question. Today's generative AI works very good on languages and text and 2D images because they are well-structured data. On the contrary, 3D is unstructured data, right? And also it has geometry inside it. So the spatial context inside it. So it induces a higher level of complexity due to that. And the diffusion model directly text to 3D itself is a research challenge today. Although it has solved the problem of 2D generations, it has a problem in generating 3D because of the spatial context. Now, the way diffusion works is learning a probability distribution and sampling out of it. Right. Now, learning a probability distributions of different body pose induced garment deformation is a hugely data-driven task. So you need to learn. So then the deformation can become as one sampler for the distribution, and the distribution is encompassing all the possible garment deformations that one could have. That's one naive solutions. But obviously, it's true that the strategy of creating the distributions out of many data are possible in the keeping the spatial context in mind, and that would be, I guess, still a open research problem because this is text, this is body motion to 4D animation, not even 3D, because it has to animate over time. So 4D generation is a quite complex process. I don't know, there are maybe 1 or 2 papers that exist today, diffusion based 4D generation. That is a future direction of research which we have to think through. How much that...
One last question from me, a quick question. There are many PhD students, master students, and even the new faculty in different universities and colleges across. So they are looking to collaborate with a company or industry like TCS. How they can reach to your group who are doing excellent, research and translation to the practice. Any quick answer is that they need to contact you or something?
Yeah, they can contact me, no problem. So we have different mode of engagement. We have pre-doc engagement, post-doc engagement. We also have internship. We also have full-time hiring whenever there is a requirement or vacancy. We also have our co-innovation network, which tries to establish relationship with academia. And we also have sponsored project mechanisms based on the relevance of the project, relevance of the person. So there are many such opportunities which are there through which one can engage with our TCS research.
Thank you, sir. Anyway, one question is there, how GARSIM model deals with the garment materials? Probably you have already dealt with. Anyway, you can just repeat how GARSIM model deals with the garment materials.
Yes, there are materials properties which are also being induced as a floating point number, as a material coefficient into the neural network encoding process itself. So whenever we are inducing the deformations for predicting the acceleration and velocities, we are also using the same materials, same garments with different materials and trying to produce different velocities or different acceleration in training processes. So in the test time, if I given a garment, I give a material properties, the neural network knows how to deform that particular vertices given the material properties.
Thank you very much for your enlightening talk. Another question has come up. Just let me see. If the trace is loose, then how you are tuning the skinning coefficient?
If the, sorry, say me again. Pardon me.
If the trace is loose, then how you are tuning the skinning coefficient?
Okay, so no, we are not tuning the skinning coefficient. We are just using the skinning coefficient to initially deform the garment. Even if the garment is loose, the skinning coefficient can be applied there, but the deformation will not be correct. But we are going to get initial deformations, which our physics-based neural network is going to act upon those initialized garment and try to correct those deformations. We are not changing the skinning coefficient in the pipeline.
Thank you very much. So I hope everything has been covered. So now I'll hand over to Somnath for the remaining part of the session.
Thank you, sir. Thank you, Dr. Bhowmik, for this wonderful session, and Professor Bhattacharya for chairing this session. So now let us move forward to the towards the end of this today's lecture session, the third lecture session of IEEE CIS. Before I offer the
just to interrupt you, in fact, for the participants alone, there has been a link for feedback, for giving your feedback on the session in the chat box. In fact, it has been shared by IEEE CIS Kolkata chapter itself. So I would request all the attendees over here who would love to have your feedback, because then that will improve our further sessions, which will be taking up in the near future. So please fill up the feedback form at your earliest convenience. And now, Somnath,
Yes.
over to you.
Yes, sir. So there is another announcement from us. There is the tentative, the fourth session of the lecture. The session will be on 31st of August, and the speakers on the fourth series of this event will be Dr. Neev Majumdar from Thermo Fisher Scientific and Professor Sudeshna Sarkar from IIT Kharagpur. So we are also looking forward your active participation from all the participants and others in that fourth event of this series. So let me now today also offer the vote of thanks. So distinguished guests, esteemed speakers, and fellow members of IEEE CIS, ladies and gentlemen, today we have successfully concluded to the third session of the IEEE CIS Kolkata series, and it is with immense pleasure and gratitude that I stand before you to deliver the vote of thanks. The memorable event would not have been possible without the valuable contribution and unwavering support from numerous individuals, and I would like to take this opportunity to express my heartfelt appreciation. First and foremost, I extend our deepest gratitude to our today's distinguished speakers, Professor Archon Mishra and Dr. Brojeshwar Bhomik. Your insightful presentations were truly enlightening and inspiring to all of us. I would also like to extend our thanks to the organizing committee, especially Professor Dipankar Dasgupta, Professor Tandra Pal, Dr. Arjit Ukil, for their relentless efforts in planning and executing this event seamlessly. Your commitment and attention to detail have been commendable, ensuring that everything ran smoothly and efficiently. I also want to extend our appreciation to our moderators, Dr. Himadri Paul and Professor Siddhartha Bhattacharya, for chairing the today's two sessions. Next, I will extend our appreciation to the audience, all participants, and all IEEE CIS members who joined us in this event. Your presence and active engagement are what makes events like this so enriching and worthwhile. We hope that you will find our the next sessions, next lecture series also very much academic and enriching. So now we are concluding this third session. Let us hope to organize the fourth event with more participation from all of you. So thank you, everyone, and good night.